Today's lesson is on parent functions. From the examples in the lessons, as well as from your previous experience working with equations and graphs, you may have already made connections between the forms of equations and functions and what the graph looks like. So in the next couple of lessons, we will examine several families of functions. A family of functions is a set of functions whose equations have a similar form. The parent of the family is the equation in the family with the simplest form. So in other words, it's the most basic of all the graphs in the function family. Parent functions are the simplest function in the function family, like we just mentioned. This is the function that is transformed to create other members in a family of functions. In this graph over here, we see three graphs. We see the orange line, we see the purple line, and we see the blue line. So the most basic of all the graphs is this orange line that you see right here. Okay, and one way to notice that it's the most basic is look at the function. This is just y equals the absolute value of x. Here we have the absolute value of x minus 2, which is obviously more complex. And here we have the absolute value of x minus 3, which is also more complex. So again, the most basic one is going to be your parent function. If we look at two more examples, we have this here where we have y equals x squared, then we have y equals x plus 3 in parentheses squared minus 2, that's the blue graph, and then the purple graph is y equals negative x squared. Hopefully you all recognize that y equals x squared is the most basic, therefore it's the parent function. Here we have, or this graph here, we have the parent function, y equals the square root of x. That's the most basic compared to y equals x, the square root of x plus 2, or y equals negative square root of x plus 4 minus 1. If we graph some parent functions by ourselves, we're going to start with a linear function. Today we're just going to look at about, I think I did, 6 parent functions. There's a lot more parent functions than this, but we're just going to start off with these 6, and throughout the year we'll add more functions to this as we go. But anyways, the first function we're looking at is a linear function. And just a quick note, a linear function is something that you've been graphing since probably 5th grade, and you've graphed it in the slope-intercept form. So while I'm going to go over this using parent functions and another way of graphing, I also understand that you've already learned how to graph a linear function, so if you continue to graph the way you already know, I am fine with that. Okay, so finding the function values. A linear function is f of x is equal to x, and we're going to test 5 critical points to find some points on the graph. Our 5 critical points are going to start at x value of negative 2, x value negative 1, 0, 1, and 2. So we're evaluating these points in the function f of x is equal to x. So So we're going to substitute this value into that function. To start with, we have f of negative 2. That's equal to negative 2. F of negative 1 is equal to negative 1. F of 0 is going to be equal to 0. F of 1 is equal to 1. F of 2 is equal to 2. And then we graph those points. We have a point at negative 2, negative 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And don't forget that any line you graph in the coordinate plane does continue forever. So don't forget those arrows on the end. Okay, using what we learned in previous lessons, we need to talk about the domain, range, increasing, decreasing, and end behavior. The domain on this graph has no restrictions on the x value, so it's negative to positive infinity. The range is also negative to positive infinity with no restrictions. For increasing intervals, we are increasing the entire time. This graph never turns direction, so our increasing interval is negative to positive infinity, and there are no decreasing intervals. End behavior is looking at the ends of the graph, starting with positive infinity or heading towards positive infinity on the x-axis. We can see that the graph is heading up. So we would say as x approaches positive infinity, the function approaches positive infinity. And as x approaches negative infinity, the function is heading down towards negative infinity. Next we have the absolute value function. The absolute value function is f of x is equal to the absolute value of x. A couple helpful tips on this. So first thing, absolute value stands for the distance from 0. So distance is always a positive value, therefore absolute value will always give you a positive answer. The other helpful tip is that absolute value, there's a v in value. Your graph looks like a v. So it comes to a point. It actually has a point either at the bottom or the top of the graph, and it looks like a V. We're going to do the same thing we did for a linear function. We're going to test 5 critical points, and we're going to test the same 5 that we started with on the previous one, or the linear function. Negative 2, negative 1, 0, 1, and 2. We're evaluating these values in the function f of x is equal to the absolute value of x. Starting with negative 2, f of negative 2 is equal to the absolute value of negative 2. That's saying how far from 0 is negative 2, and the answer to that would be 2 units. So absolute value always produces a positive answer. F of negative 1 is the absolute value of negative 1. Your answer is 1. F of 0 is 0. F of 1 is 1. And f of 2 is 2. Again, always positive answers. We have a point at negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. Our graph appears to look like a V, so make sure you see that sharp point. Don't curve it at the end to make sure it clearly looks like a V. The domain on this function is all x values. As you can see, this function is continuing in both directions forever. There are no restrictions on the x value. Your domain is negative to positive infinity. The range, however, this graph starts right here and then it heads up in both directions forever, but it never goes below that point at 0. So the range is going to be from 0, including that point because there's a closed dot there, to positive infinity. We have an increasing interval here, and we do have one decreasing interval, which actually starts the function. So starting from left to right, we're decreasing from negative infinity until an x value of 0. And then we change directions at 0 and increase from 0 to positive infinity. Both ends of this graph faces up. So as x approaches positive infinity, the function heads up towards positive infinity. And as x approaches negative infinity, the function is still heading up to positive infinity. The third graph we're looking at is the quadratic function. F of x is equal to x squared. This graph looks like a U. So the previous graph looked like a V. This graph looks like a U. Make sure you can clearly tell the difference between the two of them. We're going to test the same 5 critical values, -2, -1, 0, 1, and 2. We're substituting these points into the function f of x equals x squared. When I substitute -2 into x squared, we have -2 in parentheses squared, which is equal to positive 4. -1 in parentheses squared is positive 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. We can plot those points at -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And again, make it in the shape of a U. Doesn't have to be perfect, just, somehow the shape of a U. Make sure you touch all points. The domain is x values. This graph continuously gets wider forever. We would say that the domain is all real numbers. While the range actually starts right here at 0 and goes up forever. The range is from 0 to positive infinity. This graph starts off decreasing and then increases. We have a decreasing interval from negative infinity to 0. And then at 0, we change directions and increase from 0 to positive infinity. Both ends of this graph face up. So as x approaches positive infinity, the graph is going up towards positive infinity. And as x approaches negative infinity, the graph is still going up towards positive infinity. The fourth and last graph that we're actually testing points for is going to be a cubic function. And then the last two graphs, we're just going to talk about what they look like. A cubic function is f of x is equal to x cubed. Test the same 5 critical values, or x values of -2, -1, 0, 1, and 2. we're testing these in the function of x cubed. When we substitute negative 2 into x cubed, we have negative 2 cubed, which is positive 8. I'm sorry, negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. When I plot these values, I have a point at negative 2, negative 8, negative 1, 1, 0, 0, 1, 1, 2, 8. Connect these points with a continuous curve, and that's what your final graph looks like. There are no restrictions on the domain. This graph does continue to get wider. Also, this graph heads up forever and down forever. Therefore, there are no restrictions on the range, and the range is from negative to positive infinity. If you were walking on this graph, you would be walking up the entire time. So this is increasing from negative to positive infinity. There are no decreasing intervals. And looking at the ends of this graph, we can see as x approaches positive infinity, the graph goes up towards positive infinity. As x approaches negative infinity, the graph is going down towards negative infinity. Okay, in the last two graphs, we're just taking a look at them. You're going to be asked to analyze graphs like this, but you will not be asked to actually graph them at this point. You'll only be asked to graph those first four. For the fifth graph here, so again, just analyzing it, we have the square root function. So the square root function looks like this. This function starts at 0 and goes on in the positive direction forever. So our domain, again, that starts at 0. I had just said that. It does include that point. That's a solid point at 0. It's from 0 to positive infinity. And the range also starts here at 0 and goes up forever. So that is 0 to positive infinity. This graph starts at 0, but then it does increase. Therefore, we can say that we have an increasing interval from 0 to positive infinity. It's the first time we're putting a number in our increasing and decreasing interval to start with. Usually we start with negative or positive infinity, but in this case, make sure you have that 0 because that is where we're starting. All right, with that said, obviously you'd be walking up the whole time. This graph is just continuously increasing, so there are no decreasing intervals. And for end behavior, so there's only one end of this graph. There's only one end that shows it continues forever, so there's only going to be one end behavior. And that end behavior says that as x approaches positive infinity, the graph is heading up towards positive infinity. There is no end of the graph over here anywhere. That graph does not head in the negative direction. It stops at 0. So we do not include that. We only say as x approaches positive infinity, the function approaches positive infinity. And we're going to get rid of that bottom line. Lastly, we have the cube root function, which is I almost said square. The cube root of x. The graph looks like this. There are no restrictions for the domain or the range, so we have negative to positive infinity for both. If you are walking on this graph from left to right, you're walking uphill the whole time. We only have increasing intervals, no decreasing intervals. And we do have two ends on this graph. As x approaches positive infinity, The function is slowly, but it is heading up towards positive infinity. And as x approaches negative infinity, very slowly the graph is heading towards negative infinity. Okay, stapled to your note packet, you have some graphic organizers that you can regraph. So it's these same functions. If you want to regraph them and cut those up for a graphic organizer, make like a little booklet with all of your parent functions. We do this a lot throughout the entire school year. So there's going to be graphing parent functions in every unit for the rest of the year. It is a good idea to make sure you understand what they all are. All right, email me if you have any questions on this lesson, and other than that graphic organizer, there is no other practice with this lesson, so there is not going to be a Go formative today.